Okay, well, thank you, Adrian, and thanks for the invitation to this. It's really my distinct pleasure to kick off the second week in the probability series for the conference in memory of Charles Stein. And last week, for the statistics portion, a lot of speakers told personal stories of their interactions with Charles. So I combed through my memory, and nothing particular stood out regarding my interactions with Charles, but the theme emerged, which is the theme that all the speakers will also express when they speak about their recollections of Charles, which is how generous and how gentle he was, and what a kind person he was. And I do have recollections of showing up at Stanford, just kind of at a moment's notice, visiting somebody else and thinking I'll knock on his door. And he was never busy, so he would never not have time to go to lunch, and he's just always a very patient person. As far as his gentleness, I think it was said best by Charles's son at Charles's 90th birthday celebration. Maybe some of you were there and recall the situation. So the son was going to tell the story when he was a teenager, and he was really spoken to by his father in the strongest possible terms. And Charles, the father, was, at this one instance, was at this point really going to draw the line and put his foot down. And the situation was the younger Charles, I imagine he was maybe 16 or like this, he was going to take the car out at night to some big vacant lot, and maybe it had rained and maybe it had even snowed. And he was going to see how he could get the car to slide and to spin and do all kinds of tricks. And when he was done explaining the plan, Charles turned to him and said, "I wouldn't recommend that." The strongest language he ever heard from Charles. Okay, so to the topic at hand. So I'm going to be discussing the Dyckman distribution. And it's a pleasure to be in an auditorium where many people have actually heard of the Dyckman distribution. I know that Andrew, for example, has tangled with the Dyckman, and there are others whose names will be mentioned in connection with the work I'll present. So I usually say this is a very unknown, and probably none of you have ever heard of this distribution. I'll go over some of the basics anyway, but it's an unusual distribution, and we'll also look at applications to quickselect kind of sorting, and probabilistic number theory, and see how Stein enters into all of these topics. Okay, so Dyckman, the story with the Dyckman function began in 1920 in a publication in what looks to me like an obscure Scandinavian journal, or even if you don't know Scandinavian, it's a Swedish journal. And even if you don't know Swedish, then you can see the title of the journal is some kind of like mixed bag of astrophysics, physics, mathematics. And this was the only paper that Dyckman ever published, as far as I know. And I searched the internet and find no information about whether he was an academic, but this was the only publication. So he was looking at this number theoretic function. So let's look at the number of integers k less than or equal to x, such that the maximum prime factor is less than or equal to y. Okay, so just kind of to parse this out a little bit more, we're not going to use this just very much. So if we have like x is 7 and y is 3, then let's write out all the numbers, starting at 2, 5, 6, 7, right? And then we see which of these are composed of prime factors that are 3 or smaller, right? So 2 and 3 and 4, yes, right? 5, no. 6, yes. 7, no. So this function is 4. Okay? So there's this number theoretic function, and what Dyckman did is he looked at a certain scaling of y in x. Let's take a positive and look at this scaling as y changes like x to 1 over a. And what he discovered was this is asymptotic to x times rho of a, for rho being the Dyckman function. Okay? Now the Dyckman function is a function which he showed would satisfy the following differential delay equation. Okay, so we have this kind of differential delay equation, and you need a boundary condition in the unit interval, right? So what you're going to do is you're going to specify this here as something. I don't know. Let me make it a constant for now. So you specify here as a constant. Let's say in the unit interval. That tells you what it is in the unit interval. Then you get to go one one interval forward, because now you know what it is in the previous interval, and solve this differential equation. So for tau equals 1 is the Dickman function. If you scale it the right way, you get a density function. Okay, and that's the Dickman distribution. So this is the density function. Okay, now this density function to me is a bit scary, right? So I don't want to deal with this density function, right, if I'm going to prove things about the Dickman distribution, right? I want to have another avenue by which this distribution is more tractable. Okay, and this is what Stein's method gives us, right? So of course I can't bury this completely. There's some complexity here, right? So it's going to have to come back and bite me somehow, but we'll see that it just bites me a little bit, right? So what's nice, right, in Stein's method is you can look for characterizations of distributions. So size bias is going to enter into here. So let's recall that transformation, really. So let's take a W, which is non-negative, and let's say that it has a mean mu, which is non-zero and finite, right? Then we can look at the distribution that's characterized by the satisfaction of this identity for all, let's say bounded continuous functions, if you like. So mu expectation f w size bias. Okay. All right. So we can play games like, for example, so size bias makes a random variable stochastically larger, right? I mean, it's easy to see. It pushes it out. So what if we made it larger by size biasing it, and then we made it smaller by subtracting 1? Okay. And we could ask, is there any, say, non-negative integer value distribution for which we are back where we started, right? So is there any distribution for which you size bias and you subtract 1, then you're back where you started? And I think we all know this is the Poisson. Right? So the Poisson does that, right? Suppose you were to ask, what should we do? Let's size bias, and let's multiply by a uniform. So we size bias, and we make it bigger. We multiply by a uniform, we make it smaller, so maybe there's a chance of having a fixed point, right? So what would be the distribution? Is there a distribution for which this identity is satisfied? And Adrian knows the answer, and it's the exponential, right? Many people know the answer, but you're sitting there. Okay, now suppose we keep playing this game, right? So maybe we double size bias, right? So maybe we have expectation WFW is expectation W squared, expectation FW, so it's square bias, let's say, so by the square. Right? So what happens? So what if you take double size bias and multiply by an independent uniform, and are you ever back to where you started? All right, and the answer is the normal distribution, right, satisfies this identity. Right, so these give us different kinds of ways by which we can, let's say, characterize distributions. So let's keep playing the game. What if you take your W, so let's take a W which is non-negative, right, and then you add 1 to make it bigger, and then you multiply by a uniform to make it smaller, right? Do you ever have a distribution that ends you up back where you started? And the answer is yes, and that's the Dickman distribution. Okay, now I think that's a nicer characterization than dealing with this differential equation that goes on forever on the line, right? So here's another, right? Suppose you take a random variable, and we know that the size bias, right, is stochastically larger, right? So the size bias will perhaps equal in distribution to something W plus uniform, right? Do we ever get that identity, right? Is it ever the case when you size bias, right, that what you get, so size bias makes something bigger. Is it ever bigger in the way that I could achieve by adding an independent uniform? Okay. Is there a solution to that equation? And the answer is yes. That's also the Dickman. So the Dickman satisfies both these identities. Now, what's nice about these identities is that you can make what I call distributional transformations, right? So if you give me any W, let's talk about this one. If you give me any W, right, say non-negative or whatever, I can add 1 and multiply by a uniform, right? No, you won't stop me from doing that, right? And that creates a new random variable, W star. Right? So we can call that, say, the Dickman transform, right? And the characterization that I gave before of the Dickman being that you get back where you started, right, says that the Dickman distribution is the unique fixed point of that transformation. Right? So now we can reason as follows. We can say, suppose we have a random variable, and I add 1 to it, and I multiply by a uniform, and I'm not exactly where I started, but I'm close to where I started. Right? Well, then I'm probably close to the unique fixed point, and therefore probably close to Dickman. Right? So what's nice about these kinds of distributional characterizations is that they can be quantified. Okay, so here's, for example, quantification of this identity. So the Wasserstein, D1, Wasserstein distance between W and Dickman. Okay, so you can write the Wasserstein distance between W and Dickman is less than or equal to twice the Wasserstein distance between W and W star. Okay, so this was a result last year in EJP. Okay, so we actually have a way that we can use this transformation to get bounds for the Dyckman distribution. Okay. And this one also can give us a bound. Here we have to say maybe we missed when we size biased, right? So we can maybe allow for a little slack, right? So let's say we're going to have expectation W, f of W equals mu, which is the mean, right? So expectation W, right? And we'll have expectation here of f of W plus something, which we hope is like the uniform, and then maybe we missed by some remainder, and then some remainder. Okay, so this would be approximate size biasing, right? And let's take, if the mean is actually 1, we could write down a bound. So let's say expectation of W is 1, then in the, I'll write the one slightly weaker metric. So the 1, 1 metric where the test functions are Lipschitz and also have Lipschitz 1 derivatives, then, let's see, we have a mu. Yes, we have a mu here. So we might miss here. Let's call this mu. The real mean is 1. The mu might not equal 1, so we have to pay the price for that. So mu minus 1. And then we want this t to be like this uniform, right? So if it were Dickman, then it would be W plus an independent uniform. So we try to couple the t to a uniform. So we look at the best coupling that we can get. There's a factor of half. So the infimum of t minus a uniform for u, which is independent of W, and u uniform 0, 1, and then I have to pay the price for maybe not having an exact size bias, but having an approximate size bias. So let's look at the worst function. So the worst function, this remainder R sub f over the Lipschitz 1/2. Okay, so this is a way that we can, let's see, quantify. This bound is joint work with Chinmoy Bhattacharjee, who's sitting there trying to hide. So this is not yet published, right? In Bernoulli, but it's not yet out. So this is Bernoulli joint work with Bhattacharjee, Bernoulli. Okay. All right. So the two examples. So I want to go through these in whatever detail I can in the time allowed, right? So let me discuss the application. So these are two separate characterizations. They lead to two different Stein equations, right? And they're kind of different. So this one I'm going to apply to quickselect. So let me tell you a little bit about that. And then the other bound will apply to this probabilistic number theory situation. So let me tell you a little about quickselect. I guess I can erase here. And I'll also give you some idea of how these bounds were obtained, at least for the first one. Okay, so for quickselect, it's really simple. It's not really a sorting algorithm, but let me call it a sorting algorithm. It's the way that computationally very easy problem, which is you're given a list of n numbers, and you want to locate the mth smallest one. Okay, so there's many ways to do that. So for example, when m is 1, you're given a list of m numbers, and you want to locate the smallest one. You want to do it in the following way. So here's your here's your list of n numbers, okay? From your list of n numbers, you pick, they're all distinct, you pick one of them uniformly, and you use that as a pivot, okay? So you get to compare now whether the other numbers are larger or smaller than that number, right? So here you have your n numbers, and your pivot is here. So here's the pivot. And then I'm going to put all the numbers that are smaller on the left, okay? And all the numbers which are bigger on the right, okay? Now, if we have m or more numbers here, then the m smallest must be here. So then I'll just do recursion. I'll recurse here, right? If there's m minus 1 numbers exactly here, then the pivot must be the mth smallest. And otherwise, it must be here, right? So I'll recurse on the right. Okay, so the question is, how many comparisons do you need in order to do this? I mean, any reasonable algorithm should be big O n, right? So this is another way to get a big O n algorithm, right? So, okay, so let's let C and M be the number of comparisons made, okay, by this algorithm to locate the mth smallest number. And there's a result by Wang and Tsai in O2, which proved Dickman convergence. Okay? And the result they got was, let's take W and M equals 1 over n, so scale by 1 over n, and subtract 1. Okay, and then if M is little o of n, then you get W n m goes to Dickman. Okay, so this strange little distribution appears in this sorting algorithm. Okay, is everything clear? So please ask if there's any questions. Okay, so yeah. No. It's certain, if it's little o, it just gets killed off. Yeah. So for the bound, it's gonna it does appear, but it doesn't appear here at all. Yeah. So with this result, and in this work, then we can quantify this convergence, and the result is that D1 between, and let me just write down the m equals 1 case. So and there's similar results for the other. So this is less than or equal to some explicit constants. We get 8 log n over 2 plus 10 divided by n. Okay. And the bound is the correct rate. So you can get a lower bound, which happens at the same rate. Okay, so that gives you the right answer. Okay. All right, so maybe now back to this one for a while. I'm going to alternate a bit. Okay, so here we could look at a result in probabilistic number theory. So let's take omega n to be the set of k's. So let's order the prime numbers p1 less than p2 less than p3, et cetera. So p1 is 2, p2 is 3, right? And so let's look at the set of k's such that the maximum prime factor k is less than or equal to pn. So it's an infinite set because it has like all the powers of 2 in it, right? So just can't have prime factors that are bigger than the nth largest prime. Okay. All right. So now what? So now we're gonna pick a number at random from this set, right? So integers that have largest prime factor no greater than Pn, and we're going to do it with a distribution which is going to favor the small numbers, right? So the large numbers get chosen less frequently. So according to harmonic measure, 1 over the number. So let's take a random variable with this distribution. So mn equals m, and it's going to be chosen with probability 1 over m. And then I need some kind of normalization, which just depends on n, right? So there's the harmonic measure on this set. Okay, now what we do is we're going to take the log of mn, the right scaling. We're going to divide by the log of the largest prime, and it was proved by Pinsky in 16. Okay, this converges to Dickman. Okay, now our bound here, so we put a bound on this, which is in the D11. So we call this Wn. So Wn, so the D11 metric we have Wn against the Dickman is less than constant over log n. So we were able to show this convergence happens as constant over log n, and that the bound is unimprovable. Now, we relied heavily, very heavily on the paper, Barras, Jewell, Pauly, and Swan. And I have to say, our work is really just a slight improvement over what they did. So we tightened up the metric a bit, and we removed a constant, and we borrowed so they supplied us with all the technology that we used here. So thank you. Yeah, but it really depended a lot on their work. So just maybe this slight improvement. Okay, so now let's talk a little bit about so what's the Stein machinery behind? So these are the results, right? The bounds, and here's some applications. It's a normalizing constant. So it's whatever. So these are summable. 1 over m summable over this set. So it's 1 over the sum. It's not, this may not be summing to 1, right? So if I sum this over omega n, it's not summing to 1, but it's summing to something finite. So just divide by whatever it's summing to. Okay. Yeah, it's not obvious it converges, but it converges. So you can normalize it into a distribution. Okay, so since we're Stein people, you're probably now just dying to know what the Stein equation is, right? So what is the Stein equation for this? So of course, there's not just one Stein equation. So for these two bounds, we use 2 different Stein equations. Okay, so let's look at those. They're related. Okay, so there's a little secret here that I'll say, which is I don't want to say it, but I have to say it, which is you can get this bound without Stein's method, and it's easier. However, if you want to do this problem, right, the Stein equation for this problem is related to the Stein equation for this problem. So you have to do that anyway. Okay. So this, I'm going to have, this will be the G. G will be the name for the function in the Stein equation here. Here it's going to be an integral equation. And then here I'm going to get F, and it's going to be like a differential delay equation here. Okay, so sort of like a differential delay. It's like, I don't know what you call it if it anticipates. So we just call it different, like a differential delay equation. Okay, so here's where the sort of the complexity of the density function has to come back and cause some trouble, right? So that's going to be in the Stein equation. Okay, let me erase quickselect. Okay, so what could be the Stein equation? So take a function h of x minus expectation h of d for Dickman, and then the right-hand side will be the following for the G equation. So I'm going to write g of x minus something I'll define in a minute, ax plus 1 on g, which is an integral averaging operator. So for x positive, I'm going to define it as you like it 0. But for x positive, I'll have ax on some g is 1 over x of the integral 0 to x g of u du. Okay, so it takes the average of gu over this interval. And I claim that is a Stein equation for the Dickman distribution, and I'll show you why that's the case. Okay, so let's suppose you had expectation right here, expectation hw minus expectation hd, right? So at some point I'm going to get the expectation of this term, right? So that's the expectation of averaging a w plus 1g. Okay, good so far, right? So let's just write that down. So that's going to be the expectation of 1 over w plus 1, the integral 0 w plus 1 g of u du. Okay, that's just the definition, right? Okay, now let's make a change of variable. So let me call v equal to, let's u this way. So I want u to be v w plus 1. Okay, so du is dv, and this w plus 1 is now going to cancel, right? So we get, this is the expectation of W plus 1 goes away, right? And then the integral from 0 to 1, right? Because when v is 1, u is w plus 1, likewise 0, 0. So g of v, w plus 1, dv. Okay? Okay, so nothing fancy here, right? Okay, but now let's just interpret. So we're integrating v over the unit interval, right? So this is just like a uniform variable. Okay, so let's just say this is equal to the expectation of g of u w plus 1, which is the star transformation, right? So this is equal to the expectation of g w star. Okay, and we know, right, that when it's Dickman, w star is w. So this expectation on the right-hand side will be 0 for all g if and only if w is Dickman. That's a Stein equation, right? Okay, and so in fact, what I've showed here, before getting to the harder part, so we have g of w minus g of w star. Right? So now we could actually, we're almost to the Wasserstein bound, right? So to take H to be Lipschitz 1, then you could just use mean value theorem here, right? And you get less than or equal to G prime, right? And then expectation W star minus W, right? And then you look at the best coupling, and this is the Wasserstein distance between W star and W. Take the sup over the H's, and this is the Wasserstein distance between W and D. And I've essentially proven the bound for you, except for the G prime, right? So this is where, so now, how do we solve this? What do you do with this equation, right? So here's what you do. Here's what you do with that equation. Obviously, you're not going to come up with a very explicit solution, but you hope to come up with a solution which is explicit enough that you can get some kind of a smoothness bound, right? That's all you need. So what do you do? Okay, so take Dickman mean 0 for my function h, and then I claim that, well, formally you can see this works, I hope. So g of x to be infinite sum k 0 off to infinity, and then I'm going to take ax plus 1 iterated k times evaluated at g. H, so H. So iterate on the right-hand side on your test function. Okay? So let's suppose for the moment that actually converges. Okay, why might that be a solution, right? So what do I need? So let's take A, this is the G that appears here. I'm going to subtract off the averaging operator. So let's apply the averaging operator inside. Suppose you can do everything you want to do like that, like interchange. So now you're going to get k, you're going to go to 0, and that's just going to increase by 1 the number of times you took the averaging operator. Right? You used to do k times, but now you put a in on the left. So why don't I just reorder the sum? So this is k bigger than 1, ax plus 1 k h. Now take the difference, what's left? We're going to take the difference. The only thing which is left is the 0th term here, right? Which is just h. Okay, so this is a way, so this is how you can handle. So I think that differential equation for the density is more difficult than doing this. So this is an easier way to get around the complexity and the density. Okay, so we can actually show also that the averaging operator, so for example, if h is Lipschitz 1, right, then when you take the averaging, ax plus 1h, this is Lipschitz a half. Okay, so it smooths it, right, and because h is Dickman mean 0, the value of 0 of these are controlled, right, and so you can get the 2, right, by just taking, if this is Lipschitz 1, then the triangle inequality says the first term is a Lipschitz constant of 1, the second term is a Lipschitz constant of a half, and then it just goes down, right, by a factor of 2 every time you do that averaging. plus dot, 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 and that's where this 2 comes from. Okay, so with some details left to the reader, right? Okay. Now, so what about this F equation, right? So this is some kind of a, so G is some sort of integral equation, but I want to have this other option of using this kind of coupling, right? So let's look at what the Stein equation might be for that. So let's write, we already have, I'll borrow from here. So what if I made a new test function, or a new solution, or see what equation I get by writing f of x to be the average of g, okay? And then I'll just plug that in for, so this g, I'll just see what everything is in terms of g. So for example, you know, f x plus 1 is average ax plus 1g. It's not just going to be this term, right? So we're just going to be subtracting here. So whatever this is in terms of f, we're just going to be subtracting minus fx plus 1. All right? Okay, so this is 1 over x, integral 0 to x, gu du. So from here I get x f of x is that integral, so I take the derivative, and that's how I recover g, right? So this g of x, what is it? It's just the derivative of this, which is x f prime x, right, plus, what is it? F of x. Okay, now let me write that out in a more suggestive form, right? So let me write this as x f prime x minus fx plus 1 minus f of x, which is equal to x f prime x minus the integral of the derivative, say f prime x plus u du, right? So same thing, right? If we do that, okay, but again, here we've got this u which is appearing, right, integrated on the unit interval, right? So it's a uniform, right? So we could write this whole right-hand side as x f prime minus expectation f prime x plus a uniform. Now we know this is 0, right? This quantity is 0 if and only if we have Dickman. So this is telling me, so we started with the Dickman characterization that you add 1 and multiply by a uniform, and we're ending up with the size bias characterization, right? Because this is 0, right? If and only if you have expectation, we'll rename this to some other function. Phi of x is equal to the expectation of phi x plus u. So from one characterization, it managed to derive the other, right? This is the expectation of phi x size bias, right? So therefore, x size bias is x plus an independent u. So this gives me how I can manipulate, right? So if we're close, in other words, if we're close to this identity, then this equation is going to help me make the right hand small, right? Okay. Okay, so I don't have too much to go over the applications. Let me just try to touch on both of them just a little bit. I just have like 10 minutes, so maybe 5 minutes apiece. So first, let me demystify this distribution for you. Right? So it looks very complicated, but there's a simplification, because if you write out, let's let xk be geometric 1 minus 1 over pk, okay, then this is in Pinsky's paper. The claim is that your mn, which is a very nice form, it's just pk raised to the xk, k goes from 1 to n in distribution. Okay, seems kind of weird, but it's easy, really immediate to prove, because if you, suppose you wanted the probability that mn is some number m, well, look at the prime decomposition of m, so it's going to be pk raised to some powers ak, k goes from 1 to n, right? So nothing here has prime factors more than n, right? Pn. So the only way that mn is going to be m is if you get the right prime factorization here, and these are geometric independent, so you get the product of the probability that xk equals ak, k goes from 1 to n, right? And this is counting the number of failures, right? So in order to get ak, then I need ak failures. This is the success probability. The failure probability is 1 over pk, and that's going to be ak. You have to see ak failures, and then I get finally the success for the geometric, 1 over 1 minus pk. And now you notice that the first product is just 1 over m, right? So bring the product down here, right? And it's the product of pk to the ak, which is exactly m. And the other part was the normalizing constant that I wrote down before as this product. So this is exactly 1 over m, and then the normalizing constant, which we don't care about, but this is what appeared before. It goes from 1 to n. Okay, so I get the harmonic measure by using this trick of writing it down as geometric, right? Putting geometric number of prime factors. Okay, so now that I have that, right, I can take the log, right, and so the log, right, is going to be the sum xk pk, it goes from 1 to n, and now I can size bias this. Right? So actually, let me do a simpler example while I have a moment, right, because you can see the point in a simpler example. So suppose we're given just the sum, to illustrate the size bias method, suppose we're given just the sum Wn is 1 over n k bk. So here's a nice example, right, where the bk's are independent and they're Bernoulli with success probability 1 over k. All right, so you're getting the factor k with probability 1 over k. Right, so I always think what would happen if when I told my undergraduate class, to prove this goes to normal, it's just a sum of weighted independent random variables, right? So the limit should be normal. So if there's your exercise, go home and prove, what is the asymptotic, prove it's normal and find the asymptotic variance and see what they come back with. Okay. Anyway, it goes to Dickman, right? And we can easily show that it goes to Dickman in the following way. So we take the size bias, right? Take the size bias by, we know the rule for size biasing is you pick a sum end, probability proportional to its expectation, right? So the expectations are all 1, because k times 1 over k is 1, right? So you have a big K which is going to be uniformly chosen. So big K is uniformly chosen between 1 and n, okay? So we're going to take our Wn and we're going to throw out k bk, right? So throw out k bk over n. Then I've got to put back in the size bias version of the sum end I threw out. Okay? So I put that back in. So anytime you size bias a non-trivial Bernoulli, it's just 1, right? Because the atom at 0 is gone, right? So you put back in k over n. Okay? So before we were writing out in the theorem, which I unfortunately erased, we're writing out that we had W size bias sort of looks like W plus T, right? So this is the T. In other words, this is equal to Wn plus T. We want this T to be like a uniform, right? So here the T is 1 over n times k minus k bk over n. So I've got to couple T to a uniform which is independent, right, of W, but it's sort of already done for me, right? Because I might as well just take my k, take an independent uniform, and multiply by n and round it up. Okay, so that's the way I'm going to create my index by which to select the sum end, and that's independent of the Bernoullis and everything else, right? So this T, so what's T minus U, right? How close did I get, right? How close did I get? Well, I got 1 over n, and then nu, rounded up, and then minus u, right? And I've got, let's take absolute value and triangle inequality. So I have that plus, and then k bk over n, okay? And so basically I'm done, right? Because I actually have a bound. So t minus u, this is less than, this is just deterministically less than 1 over n, right? And in expectation, this is 1 over n, so I have 2 over n. And this is if you plug this all into this is none of those remainder terms enter because this is exact size biasing, and you actually get this as less than 1 over n in the Dickman because there's a factor of a half somewhere out in front. Okay. So 5 minutes. 5 minutes. So let me just do 5 minutes on the 4 minutes. Let me do 4 minutes on quickselect. See if I can convey the idea of what happens there. And the trick really is just what's the coupling, right? So in the G type bound, right? Then we have to couple W to W star, right? So here we have to find, that the size bias factor that you add to W is like a uniform, right? But for the quickselect, we're using the G equation, which is the D1 WD is less than 2 D WW star, where W star was uniform W plus 1. Okay? So for quickselect, and let me just focus on the case m equals 1, we want the smallest number, right? So everything's going to go into the left subtree. Yeah? So we're just going to recurse on the left subtree, right? So we're going to split it up by our pivot, left subtree, right subtree, but the smallest number is always going to be left subtree, right? Or the root, there's nothing in the left subtree. So so here's the picture. We have less than, we have greater than. Okay, so we can write C sub n, which is the number of comparisons, right? Well, first we have the pivot. Okay, there's no comparison, but then you have to compare the pivot to all the n minus 1 numbers in the list. So you get n minus 1, right? And then you get however many were in the left subtree. You got to do it again, right? So the recursion says now take C on some uniform number. Right, so V1 is uniform between 0 and n minus 1, right? You could have nothing there, or all n minus 1 numbers, not the pivot there. Okay? So that's all you know, basically, about it. Right? Okay, so Wn, the right scaling, right, is 1 over n Cn minus 1. Okay? And let's just write out what that is, and I can show you the coupling and leave some details for later. So Cn is n minus 1 plus C. Well, here's actually, I want to write something a little more explicitly. So let's let U1 be uniforms, or UK. So I'm going to look at an independent sequence of uniform variables that go on forever like that. Okay, so that I can recurse on the same sequence. Okay, so every time I do an iteration, I'm going to use up one of those uniforms and I'll shift the sequence over. Okay? So I'm going to write this as so let me write C of n, starting with the U1, is n minus 1 plus C, and then I'm going to take n U1, round it down, right? That's going to be my V1, and then I'm going to shift the sequence over. Okay, so U2. Like that. But that's all I know, right? That's all I know. So I get n minus 1 comparisons. Then the left subtree is of this size, and whatever it requires is going to be done with that randomization given by this uniform sequence. Okay? So Wn is 1 over n Cn U1 minus 1. So it's 1 over n minus 1, just write it down. C n U1 U2 minus 1. Right? And then luckily, right, so this minus 1 and this cancel, so those all cancel, and then you end up with 1 over n C nu1 u2 and then minus 1 over n. Okay, so now what about the coupling, right? How are you going to couple this together? With what? So I need some copy, right, that's going to work well, make this small, so it's very simple. So what I'm going to do is I'll take Wn prime. So I'm just going to shift the sequence over here. 1 over n Cn u2 minus 1. So that also has the same distribution as Wn, right? Okay. And then what do we need to do to get Wn star? Wn star is going to be a uniform Wn prime plus 1. I'll make that u1. When I add 1, this one cancels with this one, and I get 1 over n u1. Right? And then Wn prime, Cn u2. And then you can kind of look at these, and you can, I won't go into detail, But if you look at these, you can kind of see that they're pretty close in some sense, right? So I'm going to take the difference, right? And this one says I'm going to cut the list down by uniform and then do the sorting, okay? And this one says, where is it? I'm going to do the sorting and then whatever the number of computations is, I'll cut that down by uniform. All right, so this kind of gives me the reason that these two quantities are close. Okay, so you can get a recursion for the difference, and I don't have time to show the details, but it's not much more difficult. The key is just exactly this: to couple these together in this way, and then get a recursion for the expected difference. Okay, so hope that tells you something about the Dickman you didn't know before, and how Stein works so well in this example. Yeah, so there... Other type of what? Distances? There are other type of bounds in that you... So the answer to the question I thought you asked, which is you can use different distributions other than like the geometric. So you can construct examples where it works, where you just pick the primes according to something else. But the best we were able to do was the D11 distance. So it's an open question then if you could do Wasserstein there. Right, so we would like to improve our bound, the D11 bound in that probabilistic number theory from D11 and not require that Lipschitz derivative on F. Yeah. No. What's that? Yeah, I know you have. These are the kind of sums that arrive in your assemblies. It's what? Oh no, we weren't able to. We actually went the other way. Making more constraints on the test function to do the number theory problem. So after we looked at the distribution, we're sort of happy with Wasserstein. So we don't know how to do total variation, but it's another open question if you could do it this way. Right. Yeah. I don't think so, because I don't know how to solve the F equation any other way. So it's got this kind of, it's back to like what the density looks like, right? It's got this x plus 1 term in it, so it has this shift over, and I don't know. So I was very happy that I could go from G to F, but I don't, and that's exactly, I don't know if I said it in the talk, but right, so we get the bounds on F by just getting bounds on G, and then applying the transformation that gives you F from G. Yeah.
That's more conceptual, something I don't understand. You have shown us all these transformations. You take a distribution, you do something to a new distribution. But in the case of the one using the size bias, equals W plus C, the one is you take a distribution with size bias and subtract it before.
Yeah.
But that's the actual transformation, right? Why is there a reason to do that?
Yeah, because you sort of don't know how the uniform is going to appear. You've got to allow for the ingenuity of the person who's using the result to come up with the right uniform that has the smallest distance. What is given to you is this T, right? So the T is like this, right? And then you've got to figure out how this is close to a uniform. So you can't subtract the uniform because you don't know what the uniform is going to turn out to be.
So I guess once you have that, you could reformulate it in terms of the standard data, transformation.
Yeah, right. Exactly. Yeah. If you knew the U, then you could subtract it. Yeah, you don't know what's going to appear there. Yeah.